Buckle up, boys and girls. You're about to learn the most metal piece of math you've learned so far, the annihilator method. Basically, this is an upgraded version of our method of undetermined coefficients, where you find some operator, we'll call it A for annihilator. We take our operator A, we apply it to the right, well, really both sides of our equation, but the goal is to turn the right-hand side of our equation to 0. We annihilate everything that's there. And then the idea is when that is applied to the left-hand side of the equation, you build a larger characteristic polynomial, which you can solve through normal methods. And this allows you to figure out what your solution to the whole differential equation actually looks like. So we want to think about characteristic polynomials. When you solve any polynomial, you're finding the roots. It can have kind of three different forms. So you could have unique roots. So all of your roots are different. R equals some value is our root. And the solutions that are associated with this kind of root look something like this. The function is some constant a, e to the r t. We have an exponential form there. We could have repeated roots, where we can, if we get r1 equal to r2, then a e to the r1 t is a solution, but we also need something to go with that first solution that's linearly independent. And so to accomplish that, we usually take our exponential and we multiply it by a linear factor t out front. We have the same root r1, but it's multiplied by this linear factor. If we had repeated roots r1, r2, r3, r4, we would just multiply each one by another factor of t to get a quadratic and a cubic and so on as that goes down. If we have complex roots, where we're dipping into the imaginary here, r is equal to some real part alpha plus an imaginary part beta. Now, if it's completely imaginary, we get some sort of solution that looks like a combination a sine t plus b cosine t. But if they are completely complex with both a real and an imaginary part, the solutions can look a little more daunting, as even some polynomial a t to the k power, it can be any power depending on how many times these complex roots repeat, times an exponential alpha t, that accomplishes the real part there, and then our imaginary part picks up a sine or a cosine. So we have sine beta t. Heck, we could add a cosine beta t to that to just cover all our bases. So these are the kind of functions we can get from solving a characteristic polynomial. If our differential equation on its right-hand side is equal to things that look like this, exponentials, polynomials, or trig functions, sines and cosines here, we can use the annihilator method to build an even bigger characteristic polynomial and then essentially look at the roots of that guy and solve the rest of our equation. So how do we annihilate these things? We want to apply some operator, a, that when I act it on this exponential, I get 0. Well, how do I do that? One way to do that would be to take a derivative, d, and then subtract away the root r. This is the operator here, d representing a single derivative minus r. When I apply that to the function, I'm going to drop the constants now just for cleanliness, on e to the rt. Well, what do I get? The derivative acts on it, and I get an r out front, as the usual rules there. So I get r e to the rt minus this little r here is just a constant root. That multiplies the function when we distribute it through, and we get another root e to the rt there, which, hey, look, that's the same thing as that. It equals 0, just like we want. So the annihilator operator for an exponential function is a derivative minus a constant, the root. That's the coefficient of the t there in the argument. So that's our annihilator. This kills the function, or so we say. We can build similar operators for things like repeated roots, where now, I'm just going to give you this, for x to the k, e to the rt, your annihilator operator is going to look like d minus r, but we're going to put that to the m power. And the idea is that k equals m minus 1. So in other words, if m were 2, if this were squared, this would just be x to the 1. It would be a linear x out here, which corresponds with our idea of repeated roots. If we have repeated roots, we would have, the root squared. And so we need this extra factor of x to take care of that. If this were cubed, then k would be equal to 2. We had to have a quadratic factor. So x is always going to be 1 less than the number of factors you have over here. If we have sines and cosines, sine beta t or cosine beta t, we want to have a root that looks something like this. We're going to have d squared plus beta squared. And the reason that this works is that sine and cosine have the interesting property that when you take two derivatives of them, that's what the squared means, you're doing the derivative operator twice. You're taking the second derivative, that they are equal to themselves multiplied by a minus sign times their argument squared. So that constant comes out front twice since you've taken two derivatives. So I get the second derivative here is going to give me, negative beta squared sine squared, the thing I started with, plus beta squared times sine beta t, and that should annihilate and get us 0. So we're exploiting the property that sines and cosines after two derivatives are the negatives of themselves up to a constant. And then finally, if we just mash all of these together, the worst case scenario, as it were, x to the k, e to the alpha t, sine or cosine beta t. I'm just going to write cosine. It could be sine as well. We kind of just put them all together. We're going to take our root d minus alpha. That's the real part of the complex root there. We're going to square that. So we kind of shift the d here for the cosine over by the real part of the complex root, and then we add that beta squared there. So our worst case scenario, it looks just like the derivative operator, squared, and then this is going to be to the m power again, if it's a repeated root, for example. So if this k were 2, we would only need 1 power, but if it were 3, we would have to square this to make that work. So these are our annihilator operators. This is our team to get rid of any nasty looking things on the right hand side and apply the annihilator method. So these are what we want to be aware of. Our exponential, we have an exponential times some polynomial factor. We have trig functions in this form, and then we have our conglomerate here. Put them all together, we have, everything all at once. So how do we do this? We have a differential equation on the left-hand side. That doesn't matter right now, but that is going to be equal to some function. Let's say 6x times e to the negative 4x plus 5e to the x sine 2x. So here we have two inhomogeneities on the right-hand side of our differential equation. If we wanted to solve this using method of undetermined coefficients, we could do that. We could guess something that looks similar to this, but the annihilator method has these really nice forms that we can just assume that the solution is going to take. So we ask, what kills this function? What operator will annihilate both of these together? Well, the nice thing about these operators is that they are linear. So if we can figure out what annihilates this term separately and this term separately, the overall annihilator is going to be the thing. You just multiply those two things together. It doesn't matter that they will commute for functions like this. And so, if one of those two factors makes this go to 0, it doesn't matter what else you're multiplying it by, and the same goes for the other one. So we look at our forms here. We have, for our first term here, we've got an x times an exponential. So what I want to do is find the form that matches that. That's our repeated root form up here. And we're going to write, we only have a linear factor, so m should be equal to 2. We will get d plus 4, negative 4 being our root there. So d minus minus 4 gets us the plus 4, and we're going to put that squared to match the linear factor there, one more than the linear factor. This other one here is an exponential times a trig function. So we're going to use this form here, and this should just end up being d minus 1. 1 is the root in the exponential there, squared plus 2 squared is my argument here, gets us 4. And it's only, there are no polynomial factors here, and so it's just this. There's no power here. If we had an x out front, then we would need to put a 2 here to correspond to that, but we don't, so we're good. So we have our two individual operators here. The overall operator that will annihilate this right-hand side is just the product. So we're going to define our annihilator operator A as just the product of these two. D plus 4 squared times the quantity d minus 1 squared plus 4. And I would leave it just like this. I wouldn't try to FOIL or factor anything to make it, one overall polynomial. You're generally going to want to look at the factors that you have, and that will motivate how you generate the rest of your solution when we do this for real, right now even. So that's our annihilator for this function. Next up, we're going to try to use the method of annihilation to solve the following second-order differential equation. Method of undetermined coefficients will do the equation we're about to do just fine. We're going to do just second order here for timeliness, but the beauty of the annihilator method is it takes those undetermined coefficient type solutions and it extends it up to higher order. So this will work for things like 3, 4, 5th order if you were so brave and daring. We're going to do 2 for now because we don't have that much time. So we're going to look at the simple equation, y double prime minus y equals x times e to the x plus sine x. When we look at this function, this is a second order equation. So the way we would typically solve this is first we would look at our left-hand side and find the corresponding characteristic polynomial. I'm going to write this in terms of the operator d for derivative, and we'll just pretend like those d's are roots or some variables we could actually solve for. It kind of works out the same way. So we have d squared minus 1 acting on some function y. We've rewritten this in operator form, which is just a different notation where we have d acting on y, or d squared acting on y minus 1 acting on y is the same thing as saying second derivative minus the actual function itself, y. If we're pretending like d is a variable, well then the roots of this characteristic polynomial, if we kind of factor this out, we get d minus 1 and d plus 1. So these are two unique roots here. We would expect the solution to the homogeneous equation to look something like c1 e to the x plus c2 e to the negative x, just exponentials corresponding to each of those unique roots, 1 and negative 1. Now, we got the homogeneous equation figured out. Now we want to figure out what operator annihilates this entire right-hand side. And we can do it bit by bit. We've got an x times e to the x. That matches with this form here. And so we're going to look at the root. The coefficient of the exponential is just 1. So this is going to go to d minus 1 squared. The squared takes care of the linear x out front. The sign needs this form up here, a second derivative plus the argument squared. Here inside the argument, we just have 1x, and so we're going to get d squared plus 1, like so. So those are the two annihilators for each term. We multiply them together to build the overall annihilation operator d minus 1 squared times d squared plus 1. We can now apply this to the operator we already had there from turning it into the characteristic polynomial. And essentially what we end up with was when you act this operator on both sides of our equation, you get this really complicated looking characteristic polynomial times y equals 0. And then essentially you're kind of cheekily solving a new homogeneous equation, which is in fact really the particular solution that we want to find. So let's apply that operator to both sides. And what we end up with is, we'll just cut to the chase and say the right-hand side is 0. We apply a onto the left-hand side. We get d squared plus 1. The d minus 1 squared mixes with the d minus 1 that's already there, and we get d minus 1 cubed times d plus 1 times y. So now, if we can find the roots that go to each of these factors and their corresponding solutions, as usually goes with a characteristic polynomial, we can build the overall solution to this equation. So we'll just take them, one by one from, I guess, right to left, the order that they're acting on y. So d plus 1 is just a normal root, so we're going to get y is equal to c1 e to the negative x. Then we have 3 factors of d minus 1. So one of those comes from the actual differential equation themselves. The other 2 come from the annihilator for x times e to the x. So we get plus c2 e to the x. That one's from the actual function, so that matches with our homogeneous solution so far. And then the next things that are going to come are all going to be from the particular solution on the right. So we're going to get plus c3 x e to the x. So that matches with the first of our annihilators. And then the second of our annihilators gets us c4 x squared e to the x. And then finally, this d squared plus 1 goes with sine or cosine. I'm going to write both of them just to cover our bases. Depending on how many derivatives you have, if you have third or first derivatives, the cosines might actually matter. I'll cut to the chase and say here they won't, because sine is y, and if I take another 2 more derivatives of that, I'll get back to sine. There's no first derivative here, so the cosines won't matter, but it's just a good habit to cover all your bases and keep the cosine there. So we have c5 cosine x plus c6 sine x. We have 6 different coefficients we need to find. These first 2 are from the homogeneous solution, and you can get the c1 and 2 by looking at your initial conditions. We don't have any here, so our final solution should be able to help us find C's 3 through 6. but we'll still have C1 and C2 undetermined until we get initial conditions. These remainders, as I just said, are going to be from the particular solution from our annihilator, and we can find those through direct substitution. Find C's via substitution. The nice thing is, by principle of superposition, we don't need to take all 6 terms to make that happen. We can just take the particular part, take the 2 derivatives we need to figure out what y prime, double prime looks like, and then subtract the original function from that. Then we're going to match terms. We need a term that has an x times e to the x, and then we need terms that have sine at the end of the day. So that will help us motivate what these 4 C's are going to be. So let's take a little time to do that real quick. We're going to start by defining our particular solution as C3x e to the x plus C4x squared e to the x plus our sine and cosine combination. We'll take the first derivative, and what I'm going to do is I'm going to note that I have an e to the x on both of these terms. I'm going to factor that out and kind of treat this as a product rule, an exponential times a polynomial, C3x plus C4x squared. So when I do that, I get e to the x times that polynomial. Derivative of e to the x is just e to the x, so that just stays the same, plus now e to the x stays the same anyway, because I'm taking the derivative of the polynomial part now, and I get C3 plus 2C4x. So that's the product rule for those first terms there. Now I'm going to do the sines and cosines. The cosine gets us negative C5 sine, and then we get positive C6 cosine x. Once more with feeling, we will take the derivative again. We can kind of do the same thing, polynomial times exponential for product rule. We kind of get this repetition going on as we find that the first 2 terms are exactly the first 2 terms of the first derivative. Now I'm going to apply product rule on the second term here and get e to the x C3 plus 2C4 plus e to the x times the derivative here. The constant goes away. I'm left with just 2C4. And then I should just get my sines and cosines back the way they were, but with the signs flipped. So minus C5 cosine x minus C6 sine x. So we've got a doozy here. I want to subtract y from the second derivative, and I'm going to match terms. So the way we're going to do this is we have constants times e to the x. I'm going to collect all of those and then build kind of what we're matching here. So the constants, we can kind of find them. There's one, there's another one, there's another one. So we get C3 plus 4C4, that's the 2C4 and another 2C4, minus the constant term, we don't have one. And that's fine because on the original right-hand side of the equation, there was no e to the x, there was an x e to the x, but this should equal 0 to match that coefficient there. When we look at the linear ones, which is one of the inhomogeneities we actually have, we can again match those terms. I have a C3 plus another C3, plus 2C4x. These are really messy, so you really got to go in and find the terms that matter, and then we subtract a C3 from that. And that should equal 1. I had left off the x here. So let's revisit this. Constant. Make sure we have this good. There's constant C3 and another C3. So we get 2C3 plus 2C4 equal 0 because there's nothing from the original function. And there's no 0 on the right-hand side of the original differential equation. Now we look at the linear terms. We get C3 plus 4C4, 2C4, 2C4. 4C4 equals 1. We have an x e to the x term. Then finally, the quadratic. Oh, we're going to subtract the C3 from the original equation, which means that the C3s go away, and hey, we can just actually solve for C4. C4 should be 1/4. The quadratic term, we have just a C4 here, and we're going to subtract the C4. So that actually, it doesn't actually get us any new information. We can, however, use the C4 we found from the linear part matching and put it up here. So we get 2 times 1/4 is 1/2. And so that means that C3 is going to be 2C3 equals negative 1/2, or C3 equals negative 1/4. Now the last things to compare are these sines and cosines. We get a negative C5 minus a C5 equals no cosines that we had to begin with, and so C5 should just be 0. We look at the sines, however, we get negative C6 minus C6 gets us negative 2C6 equals, we only had one sine, so it has to equal 1. That means that C6 equals negative 1/2. So with these coefficients all determined now, we can show that our particular solution is equal to C3 is negative 1/4 x e to the x plus 1/4 x squared e to the x. C5 was 0 minus 1/2 sine x. That's our particular solution. The overall solution y is going to be equal to C1 e to the x plus negative x plus C2 e to the x plus our particular solution. I'm not going to write it out again. But that would be our 5-term monstrosity that we just figured out. If we had initial conditions, we could do the normal thing of setting this and say its derivative equal to the given values and determining from that system what C2 and C1 have to be. I think this is good enough for now. So that's our annihilator method. The trick is you're going to look at your equation. You're going to find functions that annihilate however you spell that, annihilate inhomogeneities. And that's just a really fancy word for functions on the right-hand side of your equation. You take your differential equation in standard form, whatever order it's in, and it's equal to some function of x or t or whatever your independent variable is. So you find functions that annihilate inhomogeneities. We look at the different forms for exponentials or trigs or products of those. You're going to multiply those functions and apply to both sides. The result is a bunch of factors of a characteristic polynomial equal to 0. So now essentially you have like a new and improved characteristic polynomial, where if you find all the roots of that, whether they're real, repeated, or complex, you should know what the solutions look like. So you can write general solution. Give them a salute while you're at it. You write the general solution with undetermined coefficients. You can determine coefficients of particular through substitution and matching coefficients, matching like terms. And then finally, should you have an initial value problem, you can get the coefficients of the homogeneous solution with initial values, IVs. And that's how you break it down. That's how you annihilate those differential equations.